Okay, so this is a device that is capable of generating electrical energy. Okay, so we can get current flow from chemical reactions. That's our basic definition. So to do this, okay, so getting current flow from chemical reactions, e.g. maybe making a battery, we need something called two separate half cells. This is a word I didn't really use last time, okay, but we have talked about half reactions now, so it maybe is making some sense. We have two half cells here. These are two examples of an electrochemical cell. We have this galvanic cell where some spontaneous reaction drives the movement of electrons, okay? In this case here, as the zinc gets oxidized, okay, the zinc ions go into solution and the electrons flow this way over to the copper bar, okay? So that copper in solution can come up and deposit on the copper electrode or copper cathode here. An electrolytic cell, here we have some external power supply that is driving a non-spontaneous reaction, right? This is the only one we're going to talk about in this class. We're not going to talk about the other one, okay, for our course and for our textbook. Okay, so we're only talking about this situation up here. So we have is electrons being released from the zinc, okay? So we have, in this case, we have a zinc bar in our copper solution, which is the situation we just saw on the previous slide. The zinc ions pop off and go into solution, and the electrons flow through the wire over to the copper bar, where copper in solution comes out of solution and deposits on mixed solid copper on our electrode. Okay, this is called, these two are called electrodes here, and these are two half cells of our total battery or our total cell. Now, one of the things we need to complete our circuit, okay? And that's what's shown here, this semi-permeable bridge, or here it's shown as a salt bridge. Basically, this is something that allows the flow of our sulfate ions, but it's not going to allow the flow of our metal, okay? The reason being here, as zinc ions keep popping off into solution, the solution is getting a really positive charge, right? Because the electrons are going over here. And as all the copper is coming out of solution, this is getting a really negative charge. And so in order to accommodate for this charge buildup that would happen, we put a bridge in where the sulfate can diffuse and flow, whichever direction it needs to flow, depending. Right? So a very annoying thing for me, the electrons are flowing this way, okay? But our definition of current is the direction that positive charge would move. So current is flowing the other way, just by how we define it. And the important thing to remember is that when current's flowing, it depends on what our charged particles are that are moving. So for us, and with our metals, the charge that's moving happens to be electrons, which are negative, which is why it's the opposite direction. But you could have positively charged molecules that move in a different situation than what we're showing here, okay? So current would go this way, that's why the arrow points this way, and it's just saying there wouldn't be any current flow here because eventually this would stop. We don't have the connection we need. Okay? But this is the direction that the electrons want to go. Any questions on that?